we're going to be talking about the B movie for Newton's 3 laws. So Newton's first law, an object at rest will stay at rest, and an object in motion stays in motion with the same speed and same direction unless acted upon by an unbalanced force. Here, Barry and Vanessa are having a picnic in Barry's dream, and when Vanessa gets in a plane and crashes into a big old rock. The rock is the outside force which completely stops the plane and its speed and direction, which just destroys it. So here in the free body diagrams of the plane, you have the lift of the plane, which is causing it to stay in the air, and you obviously have the force of gravity because you can't turn gravity off. And the thrust of the plane is what is making it go forward. And then you got the big old rock that's just there. Gravity is obviously affecting it, and then the normal force of the ground keeping it stable. And then when the plane hits the rock has the normal force that stops it. And so that is why the plane is stopped and loses its speed and its motion because it was acted on by an unbalanced force. She would have to be increasing her speed at a very dangerous rate for the plane to be completely destroyed. So there is probably a bit of bad movie physics in that. Newton's second law, all these equations can be applied. The acceleration of an object is dependent upon two variables, and that force acting upon the object and the mass of the object. So here's the scene. Here, Ken and Barry are fighting, and Ken is basically attempting to murder Barry, but ends up hurting himself. So I'm going to use the equation to figure out the force of gravity, the mass, and the acceleration of the metal shower rod that hits Ken on the head. So I weighed my metal shower rod and got roughly 1.7 pounds, which we have to convert into newtons, and we know that 1 pound is equal to 4.44822216 newtons. So then, using our little field goal method, 1 pound is equal to 4.44822216 newtons. So you have to have those, and then they cancel out, giving you multiplying this times that, which gives you your 7.56197672 newtons. And since we already know the acceleration that is due to gravity on Earth, that's your 9.8. So there we can find out our mass because we just solved for the force. So rounding that, you get 7.6 newtons divided by your 9.8 meters per second squared, and you get 0.77555102 kilograms. And so that is the mass. And here we have all of the information, the force of gravity, the mass, and the acceleration. We have our free body diagrams. The shower rod is affected by gravity, obviously causing it to hit Ken on the head. And then Ken, who's in the tub, is affected by gravity and the normal force. And this is accurate because the shower curtain is affected by gravity and can fall and hit someone in the head. For Newton's third law, for every action, there is an equal and opposite reaction. And here's the sum.
Ow! What was that? Maybe this time.
Here, Barry is trying to get out from the window, yet he cannot because bees can go through windows. So when he tries to fly out, he hits the glass and bounces back. This is because the window exerts an equal and opposite force, which causes him to bounce back. So with the free body diagram, Barry the bee, he is flying, so the force of gravity is affecting him, and he's lifting himself because he can fly, and he applies a force against the window. Yet the window applies the exact force right back, which is the reaction force, therefore making their forces equal. Also, with all of Newton's laws found in the Bee movie, they're all relatively realistic, except for the plane crashing, because she would have to be increasing at a very, very high acceleration, and she would probably die, but that's kind of sad to talk about, so we're not going to talk about it anymore. So for projectile motion, I will be using a clip of the ending of Hoosiers where Ollie is attempting a grain shot to win the game. Here are the free body diagrams. Ollie, he's stabilized, he's not moving except for his arms, and the force of gravity and the normal force of the basketball court are balancing him. And then he throws the ball, which gravity is at work against it, and so is air resistance, but he applies a force to throw the ball into the direction of the hoop, which then he makes. And the velocity of the ball is initially zero until Ollie throws it at an angle towards the basket, causing the ball to speed up and be thrown to the direction of the hoop. Then the speed decreases suddenly as gravity becomes greater after the ball goes through the hoop and hits the ground. Very realistic because basketball. No crazy physics in this part of the movie. For work, as my mechanics concept, I'd just like to preface that I scribble out a lot of things. Hence that, because I mess up a lot, haha. So, here's the clip.
Here comes the pitch. And one.
Here in the movie 42, Jackie Robinson is up to bat, and we're going to calculate the work that is done by the pitcher. So to calculate work is force times displacement, but we have to find the force. And the equation for force is mass times acceleration, and the average mass of a Major League Baseball is 142 grams, and the average acceleration of the pitcher, who is throwing at approximately 92 miles per hour, we have to convert that into meters per second. So 92 miles per 1 hour, we have to cancel that out with the hour. Those cancels out. Then 1 hour is 60 minutes, and so then you have to cancel out your 1 minute with 60 minutes, and 1 minute is equal to 60 seconds, so those cancel out. And then you're left with your seconds, and then you have to convert your miles. So for every 1 mile, there's 1,609.34 meters. So then your miles cancel out, and then you multiply across, and you get this, and then that goes down to 41.1275 meters per second. And for purposes, we're just going to round it to 41.1 meters per second. And then multiply those together, and your force is 5,836.2 newtons. And then you can apply that into your work equation. See, I messed up. Your work equation is force times displacement, and for displacement, you have to figure out how far the pitcher's mound is from the home base. So then we convert it from 60 feet to meters. So then those cancel out times that. That's 18 meters. And so you do your newtons, your force times your displacement, and you get that many joules, 105,051.6 joules. Yeehaw. Here we have the free body diagram for the baseball. Once the ball is thrown, has a thrust from the pitcher throwing it, and it has gravity affecting it. And then it has air resistance going in the opposite direction, yet it does not overcome the thrust. And we have the pitcher throwing the ball, and the pitcher is obviously not floating off the ground, so gravity and normal force are balanced, and then he applies a force to throw the baseball.